Hello students, in this video we'll find the formula for the Gaussian curvature of a surface with a respect to the map. Let's consider a surface with metric first fundamental form I is e to the 2f dx squared plus dy squared. These metrics are, of course, conformal to Euclidean space, right? So these are conformal metrics. Okay, and so recall that if we have a special form, so recall from the Theorema Egregium, the Gauss Theorem Egregium implies that for such a metric, k is -1 over 2 square root e times g, of course e and g, and then the u derivative of what? The u derivative of eu over the square root of eg plus the v derivative of gv over the square root of eg, like this. Beautiful, okay? And so now, of course, for this metric, what happens? For this metric, for our metric, e equals g equals e to the 2f, right? Beautiful. So let's do the calculation now. So, of course, what is eu going to be? So e times g square rooted, so square root of eg is going to be the square root of e to the 2f times e to the 2f, which is e to the 2f, right? That's beautiful. And then what's eu? And also what? And also that eu is equal to what? Is equal to e to the 2f times 2f sub u. And then gv is going to be e to the 2f times 2fv, like so. Beautiful. And so now in particular, what do we have? So this allows us to complete the calculation. So my curvature k is going to equal to -1 over 2 e to the 2f, and then d by du of what? E sub u is going to be e to the 2f times 2f sub u divided by what? E to the 2f, of course, e to the 2f. Excellent. Plus d by dv of e to the 2f times 2f sub v over e to the 2f, like so. Of course, the e to the 2f's are going to cancel out over there, right? And so this says that k is going to be -1 over 2 e to the 2f. And then I'm going to have a 2 f uu plus 2 fvv, 2fvv, like that. And of course, the 2's are going to cancel out, so this is exactly equal to what? This is exactly equal to negative what? This is negative e to the negative 2f times the Laplacian of f, like so. Beautiful. And so now I'm going to multiply both sides by e to the 2f, and so this implies that the Laplacian of f is equal to kappa with a negative sign, of course. Negative Laplacian of f is equal to kappa times e to the 2f. And so I rearrange this equation to get the following formula. I get this following PDE. So here's our PDE. Our PDE for the curvature is that we have the Laplacian of f plus kappa, the curvature, Gaussian curvature, e to the 2f is equal to 0. And this is known as the scalar curvature PDE. So this is the scalar curvature PDE. Okay, beautiful. And so what this allows us to do is so of course here is the Laplacian of f. Okay, and so the one thing to know about this PDE, so notice this PDE, so remark, this PDE, namely Laplacian of f plus curvature e to the 2f, like so, equals 0, is nonlinear. That, of course, makes the study of it very difficult. This makes the study very difficult. At some point in the future, we'll develop a PDE playlist, right? And that PDE playlist will analyze certain classes of nonlinear PDEs which are have a certain structure, right? So the beautiful thing about this is that we have the Laplacian, right? So in other words, the Laplacian is actually very helpful for us too. And so in other words, trying to find out if I prescribe a curvature, right? If I say, here's what the curvature is, can you find a function f such that the conformal metric has the prescribed curvature? Finding a conformal metric with the prescribed curvature is a really difficult problem because it amounts to basically solving this partial differential equation, which is nonlinear, called the scalar curvature PDE. So in further videos, we'll analyze special cases of this scalar curvature PDE to see if we can get some analysis of these things, because we know that, for example, this is a non-negative expression over here, right? So in other words, the function f automatically has to, by trivial estimates, has to have some sort of superharmonicity. So there's some sort of estimates we can appeal to harmonic function theory to try to understand properties of this PDE from sort of a naive perspective, but actually finding solutions is very, very challenging, which we'll refer to further videos in the study of that matter. Thank you very much.